First on the agenda here is having an impact on the future, the use of ultrasonic impact treatment for increasing fatigue resistance in welded structures by Todd Niemann from Fickett Structural Solutions.
Good afternoon. I'm glad to be back. I had the opportunity to present yesterday. Today I wanted to talk about I used a little pun on words, having an impact on the future, because I'm talking about a specialized treatment that's called ultrasonic impact treatment. I introduced myself yesterday. I'm a principal engineer with Fickett Structural Solutions. The troublemakers, the rest of the troublemakers from our crew is way over there. What I want to do is I want to help you have a little bit of an understanding about what this technology is, this ultrasonic impact treatment, how it can impact the future of your bridges, and then give you a little bit of information on the cost benefit. What is ultrasonic impact testing? Ultrasonic impact testing is just peening, right? I've heard that. That's a myth. It's not true. What it is this is a technology that was developed in Russia, actually. The Russians were, back in World War II, they were having problems with their ships coming apart as they were going through the North Sea, because that's a notoriously very rough sea. They were getting fatigue cracks. Their hulls were coming apart because of fatigue. And they developed this technology to deal with the fatigue that those welds were seeing. It is quite highly specialized equipment. It's not something you can run down to Ace Hardware and rent, for sure. I like to call it peening on steroids. If you've ever heard of hammer peening, it's kind of an old thing that they used to do to welds. It is very similar in concept, but it's very different in results. What it does is, and how it works to enhance fatigue resistance, is that it imparts residual compressive stress into the weld toe area. This is a treatment that we typically concentrate on weld toes, where weld toes are a fatigue problem. So this, we do also, like regular peening, it does has an impact on the surface, and it does do some geometric improvement to the weld toe area, making it a little nicer contour. But the real magic is the compressive stress that it puts in. The difference that ultrasonic impact treatment has from regular peening is how the energy goes into the part. And with this, it goes, as the name suggests, it goes in at an ultrasonic frequency, and that's the impulses onto the surface are at ultrasonic frequency. So that's the magic. It does physically alter the microstructure in the area that it treats. So you have improved material characteristics as well as everything else that's happening. The way that it differs from traditional peening, traditional peening only has a very, very narrow surface effect, where the relaxation zone with ultrasonic impact treatment can reach a ½ inch in depth. That's very significant. If you've got an area that you can put residual compressive stresses in up to a ½ inch, that's the game changer. This technology, a lot of people probably have never heard about this technology. It kind of came as a topic about 20 years ago. There was a lot of buzz about it. A lot of research was done, and it just kind of faded. The initial research was done by Sagata Roy and Dr. Fisher from Lehigh. I believe that's how Sagata, what he did for his doctoral thesis was the research on this technology. It was full-scale testing. Of course, new technologies like this, nobody wants to use it unless it's endorsed by AASHTO and Federal Highway, and so that was the big chore that the people that were promoting this technology needed to accomplish, was to have full-scale testing done in the U.S. and then be endorsed by those agencies. So it is something that research was funded primarily by Federal Highway Administration. There's also some folks that have looked at this, some of our newer grads. I know that Jason Lloyd who formerly was the NSBA regional person out in this Pacific Northwest area. Some of you may know him. I know he did a lot of work with this also when he was at Purdue. This is technology that's really is very much endorsed by this new maintenance guideline for steel bridges that has recently been published by AASHTO. G14.1 is that document. If you haven't seen it, if you're interested, there's a lot of great information on there for dealing with steel structures. So how to use this technology to impact your future. As you know, fatigue is influenced by three factors. You have to have a source of stress, and that stress range is a number one factor. The number of cycles and the type of detail you have. Welded details are categorized and with different detail numbers, all researched and identified, through AASHTO, whether or not you have a B detail or a C detail or a D detail, E detail. So they're categorized. So the important part of this that I think that this technology helps us with is in number of cycles, and I'll explain that in a minute. Yes, it is true that using this technology actually increases your fatigue category. So a C prime detail treated with this technology can be rated up to a B in what it can take in cycles. An E prime detail, which are the worst of the worst, can move up to a C. So you're actually taking something that has a very finite fatigue life and basically making it infinite. No other weld treatment can accomplish this. So where are good places to utilize this technology? Lateral gusset plates is a place that this has been used. A notoriously problematic detail, two girder systems where there's a shelf plate that attaches to the bottom part of the web, and that's where the lateral wind bracing ties in. Those are notoriously a problem for fatigue. It has been used in those areas. Picture doesn't highlight where but it's that lower shelf plate. Some people call them lower shelf plates, some call them lateral gusset plates. They're called by different things. But they're known for the problems being the weld ends, intersecting welds. They a lot of times have poor welding details. They're sometimes supposed to be attached with a full pen weld, but they're not. They're attached with a partial pen weld. Sometimes they have backers, sometimes they don't. Sometimes those lower shelf plates are really located really close to the bottom flange, and so access to making that weld underneath there was really, really poor, and so you really had some not great looking welds down there. So that's an area where a lot of people that have these, they've had cracks. So a lot of times it's recommended to go and treat other locations around the bridge that haven't cracked yet, but you know that they're probably going to crack. So this is a preventative treatment that you can go in and say, I'm going to treat all my other details to prevent them from cracking, because I know that fatigue is starting in this, and we know that this is going to be a problem with the bridge. So this is the type of technology that you can use as a preventative measure. It's very another similar thing like these ends would be longitudinal stiffeners, web stiffeners, where those ends are notoriously a bad fatigue detail. This treatment would be very effective in those kind of details as well. The number one detail I think that this technology is just made for is cover plate ends. They're very common details, and this technology is just perfect for them. These are traditionally E or E prime details, so they're the worst of the worst. I'm from Minnesota. Dr. Dexter was at the University of Minnesota for a while. He was one of the Fisher proteges. We were lucky enough to have him. Unfortunately, we lost him early in life, but he told me once, he said, when it comes to cover plates, it's not a matter of if it's going to crack. It's a matter of when. And I never forgot that. And I thought that was an important statement coming from one of the nation's renowned fatigue experts. So I took that to heart, and we made policies. So the lower picture there is a cover plate that actually has cracked through the flange. Obviously, these are lower flanges, and so that is something that you can see, something you can inspect. The problem is a lot of times these cover plates are always in the top, or also in the top flange, and they're buried in the deck. You never have a chance to look at them. They're not accessible until you have a redecking project. It's the only time in the first 45, 50 years of the life of this bridge that these details, these Eprime details, are actually visible. When you're doing a redecking, it's usually a pretty elaborate process. It says that I'm investing in this bridge. I'm going to do a substantial investment in this bridge. I'm putting a new deck on it. I'm probably repainting the superstructure, maybe doing some bearing work. I'm investing substantial in this bridge. If you got 50 years out of the deck, the next one you put in, you're probably going to expect another 50 years out of it. So you're putting this bridge back in service for another 50 years, but you've got these Eprime details that are eventually the cycles in year 70 or year 75, year 80 are probably going to catch up to it, and they're going to start to fatigue. So it's an ideal time to, number one, since you haven't looked at those details in 50 years, you probably should. You should get out there. You should at least do an inspection of those while they're accessible and they're available. We like to say that you should clean them up a little bit and at least do a mag particle inspection on them. And since you're already there, you should put ultrasonic impact treatment on them. It will essentially, like the slide showed, it'll take it from a Eprime detail to a C detail, and that's almost will guarantee that they won't crack in the second year life that you have. So that all sounds well and good, right? Well, what does it cost? Usually it all comes down to that, right? Especially if you're the scoping engineer or the one that's holding the purse strings, you got to know what it costs. So doing this work, doing those inspections is a standard practice, a standard requirement at Minnesota DOT, where I've spent most of my career. It's a standard practice. So we put right in all steel redecks that have cover plates, weld inspection, a weld repair, and UIT. So I looked at cost data from the last several years, and costs ranged anywhere for both the combined inspection, some weld repair, do some grinding, clean up some geometric issues with welds and make them just to improve the shape and the configuration of them, and then to do the ultrasonic impact treatment. So that's where the cost range, and it turns out, in comparing that to the overall price of the contract, it's somewhere between 1% and 2%. They averaged under 2% of the contract cost. So it's really a minor project cost when you look at it and compared to the total. It's costs far less than repainting that bridge that you're going to do, but it's doing much more structurally to the steel and protecting it than probably the paint is for the next 50 years. So to me, that's a area, and that is a scenario that's just a no-brainer. It's just an application that is just perfect and really should be something that should be considered. So we talked about what UIT is. I like to call it painting on steroids. It's a treatment that is very effective at improving fatigue performance. It's a very good preventative strategy with bridge with both active problems and in situations with rehab work where you're trying to extend the life of a steel structure that has known or problematic details. And then the cost is really pretty minimal compared to your overall project cost. I think to me, it's a minor investment for a major structural enhancement. That's it for the presentation. I will say that we do have a booth. We have a laboratory version of this equipment here at the booth. We would love to let you grab the hammer and peen a weld, or I'll show you how to do it. Either way, if you're interested, would like to understand or see a little bit more about this technology, we have it here firsthand, and would love to show it to you. Any questions?
Once a weld has been treated and it's been painted over, is there any way for like an inspector to know that that's been treated? You know, like with Texas, they require you to put the fatigue category for each fatigue detail. And if you've treated this, but you come back 2 years, or a different inspector comes back 2 years later and says, oh, the previous inspector mislabeled this. This is an Eprime instead of a C. If
you come by, I think you can see that, I don't know if I have a good picture of that in the presentation, but it does create an impact on the surface. There is a line there. Now, if the paint gets too thick there, maybe that would be hard to see, but I do think that there's at least good visible evidence when you do the treatment. And I think in most cases that would be visible through a paint system in most applications.
Earlier you were showing the 3 welds intersecting the triaxial constraint. We've been going in and drilling that out and removing that, but are you able to use this technology instead, or is this technology one level in that mitigation? Could I get your thoughts on that?
Yeah, the intersecting weld isn't as great of application for this, particularly with, you're talking about like the hone type detail where you've got the shelf plate intersecting the stiffener. You want a positive connection to that stiffener, but you hope there's copes there and you don't have intersecting welds. Depending on that I think the true answer to that is sometimes. It would really kind of depend on what the gap is between the welds and how far they are overlapped as to whether or not you can really treat those toes. It certainly wouldn't help, but a drilling strategy there is what most people have done. So there have some that have done sort of a combination of efforts, but that's kind of an individual case scenario. All right, thank you.
This is the real one.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.